Yes. Now we are moving with a chapter called as loudspeakers, because we have terminated microphone in the last session. Now we are going to see loudspeaker. So what is loudspeaker actually? It is an opposite of microphone, right? Because from um air means what, radio waves are transferred into electrical signals. Here in loudspeaker the case is opposite. Here electrical signals are converted into radio waves, or we can say uh, the signals which are converted into sound waves. Fine. So electrical signals are converted into sound waves in case of loudspeaker, and what we saw in microphone is that sound waves were converted into electrical signal. So in that category we can say that loudspeaker and microphones are opposite of each other. Now let us see the definition part of loudspeaker. What it says, it's a transducer. Why it is transducer? Because it converts electrical signals of audio frequency into sound waves. This is very important. Electrical signals of audio frequency into sound waves of a same frequency. It is also called as output transducer or reverse transducer. Means we get an output at a loudspeaker, so therefore it's called an output transducer, or we can say reverse transducer. So as usual we should know the characteristics of it. What is loudspeakers? Efficiency, the ratio of the output sound power to the input audio. Actually these are the idealistic characteristics. We should know on what parameters the loudspeakers goes on. So first is efficiency, then second is noise, third one is frequency response, distortion, directivity, power and impedance. Actually I'm not going in detail of it, but only I'm listing you the characteristics: efficiency, noise, frequency, distortion, directivity, power and impedance, because we have moved with these words very nicely, so I will not go into the depth or repetition of it. So I will move to moving coil cone type loudspeakers. So this is first loudspeaker, a moving coil cone type loudspeaker, and its another name is PMMC type loudspeaker. Why it is PMMC, we will see in the principle. So let us work on the principle of this moving coil cone type loudspeaker. Moving coil cone type. The way we can say moving coil and cone type. So one thing is that the moving coil itself tells us that the coil is moving. Fine. And what is a cone? We have listened ice cream cone and all that. So that cone is something like a shape of a loudspeaker only, because it will be flattened at an outer end. So therefore it is a cone type. And now let's move with the principle. So principle is of there is an interaction between two things. Which are they? Magnetic field and current, right? Magnetic field and current. We have seen this in the AC motor also. If you know electrical subject, what we have studied in the first year. So what we say that there is an interaction between the magnetic field and a current in a same way as that of a AC motor. So this is the two words we should remember: interaction between magnetic field and a current. So this forms the principle of a loudspeaker. Now next is the, as from the diagram is concerned, there is a coil called as what, voice coil, which is placed in a uniform magnetic field. We can see in the diagram the the coil is there. It is shown as a voice coil, and it is called a voice coil actually. When the audio current passes through the voice coil, right? When the audio current passes through the voice coil, what will happen? There is an interaction between the magnetic field and current, as we said just earlier. Then the interaction takes place between the magnetic field and the current. So what will happen then? The resulting in a force, then the force will be there working on the moving coil, right? So due to the interaction of the magnetic field and the current, the resultant will be a force which is acting on the moving coil. Fine. Now what is this force? This force is proportional to what? Audio current. because the relationship it's a theory of relativity. The force of proportion, the force is proportional to the audio current, and hence causes the vibratory motion in the coil. So this force is going to cause what? Vibratory motion in the coil. So which makes the conical paper diaphragm to vibrate and produce the pressure variation. So this vibratory motion is what it is going to do. The paper, conical paper, that is nothing but a diaphragm, which is going to vibrate, and then because of the vibration of the diaphragm, the pressure variations in the air will happen, and that there will be a resulting what? Sound waves. So this is the phenomena. It's a very easy one. We do not have to much more ponder on it, because we know magnetic field, we know current. Because of that, the force is going to work out on the coil, and it will cause the vibration motion, and because of this vibration there will be the compression and rarefaction of the diaphragm, and because of that movement there will be a sound pressure variations in the air, and that will be resulting in the sound. That in a nutshell I can tell that. Fine. Now let us go some mathematics part of it. We have a force on the coil due to the what? Interface between the current through coil and magnetic field. So technically F is equal to B into L into I, right? So F, we have seen this. What is F? It's a force in the Newton. What is B here? Flux density. And what is I? That is a current in the amperes. So F is equal to B into L into I, right? So now we can see the diagram over here. What the diagram is telling us, we can see here important point is voice coil. We can see the voice coil which is suspended between the permanent magnet, and there is and attached to it is very important, that is diaphragm. We can see, and the above one is shell. So these are the important parameters. Then the other side is what? That we can see front suspension spring is there. Below that is we can see the denoted as a paper cone. Then protective frame. Then the terminals of the voice coil. And on the left side we see right suspension spider's spring. Fine. So these are all constructive labels of it. We should know each and every label actually. Fine. So let us see the working of it. So before that, it consists, what we see, it consists of a voice coil. We see the voice coil over here, right? Then wound on the cardboard. Then audio current is fed to the loudspeaker through the terminals. We can see the terminals, and we are feeding the audio current through the terminals. Then the coil is fixed in the magnetic field as we see. So that magnet is a pot type permanent magnet, which has a central pole and a peripheral pole. There are two poles. One is central pole and another one is a peripheral pole. The voice coil is free to move. As we see, voice coil is free to move, having a strong and uniform magnetic field. As we see, magnets are present. Because of the use of the permanent magnet, it is also called as PMMC, that is permanent magnet moving coil type of loudspeakers. Fine. Then the coil is attached to the diaphragm. We see in the diagram the coil is attached to diaphragm and made up of the paper, and it is also called as paper cone. The cone is corrugated, having a circular corrugation to increase the surface area for the better efficiency. So this circular corrugation is only for the surface area for better efficiency. Then leads, we can see the leads over here. Leads from the voice coils are cemented to cone surface, and from there these are brought to the terminals mounted on the metal frame, as we see in the diagram. Now next is equivalent circuit, as we see over here. Electromechanical transformation is there. One is electromechanical transformation. What we see, there are two transformation basically. One is electromechanical and another one is mechano-acoustical. So what it says, a repetition of the understanding. We see when the audio current flows through the voice coil placed in a magnetic field, right? Then the force equal to BLI newtons acts on the coil. The force which is nothing but a product of a BL and I, which acts on the coil and moves it to and fro. Fine. Then the paper cone attached to the coil also moves and causes the compression and rarefaction. So as the coil is moving, the paper cone is also moving. right? And therefore, what will happen then? Compression as well as the rarefaction of the cycles in the air, and thus the audio signal is converted into sound waves. So this is what happens. And at the last, we see the characteristics. Efficiency is about 5% only. It's low. Signal to noise ratio 30 dB. Then frequency response is having the mid frequencies only. Tweeter high frequency and woofer low frequency. Distortion is non-linear. Directivity is omnidirectional. Impedance is between 2 ohm to 32 ohms, and power handling capacity of these speakers lies between the few milliwatts to 25 watts for large size speakers. So this was with respect to our moving coil type loudspeaker, that is also called as PMMC. Okay, thank you. Now let us go for horn type of loudspeaker. It's a horn type, shaped like horn, and the next name of it is an indirect radiating type for loudspeaker. Technically, indirect radiation type loudspeaker it is. Means indirectly it is not, it's radiating actually. Directly it is not radiating, but it's indirect. So the name coins up to indirect radiating type loudspeaker. Now let us go for the principle. So principle is as usual, we have magnetic field, right? So horn type loudspeaker uses a moving coil in a magnetic field, as we see in the diagram. We see that moving coil is there in a magnetic field, fine, and in that unit. So what? But the case is that instead of radiating acoustic power directly in an open space, as in a traditional loudspeaker happens, what happens that the power is directly that acoustic power is directly radiated to the atmosphere or in the space or in the listener's area. But here the thing is different. The power is first delivered to the air trapped in a fixed non-vibrating tapered horn. So we are having a horn. So what is going to happen here? The power is first delivered to the air trapped in a fixed non-vibrating tapered horn, and from there to the air in the listener's area. Therefore, it is called as indirect. The form means it is going Y air trapped uh, in a air trapped in a non vibrating tapered horn, and from there it is delivered to the listener's area. Thus, it radiates sound power to the air in a space not directly from the diaphragm. So, it is also called as indirect radiating loudspeaker. So, indirect radiating loudspeaker means over here that in previous loudspeaker we have seen that from the diaphragm directly goes to the listener's area. Here it is not going to the listener's area directly. First, it is going to the first it is delivered to the air trapped where it is in a fixed non-vibrating tapered horn, right, and then it comes to the listener's area. So we let us see the construction. We see the right hand side, it is mouth, then throat, then air chamber, then sound absorbing material, then rigid mount, then we can see the coil over there, and another one is unit, and there is air chamber. So this is with respect to the diagram. So let us see how this horn type loudspeaker is. So horn type is a tapered enclosure whose diameter increases from a small value to the end called a throat, to the large value to other called as mouth. So in this diagram we can see that it starts with the throat and it ends with the mouth. So the throat is a small value actually, and it get increasing towards the mouth. So whose diameter increases from small value to one end called as throat, and to a large value other end is called as mouth. Fine. So only the thing is that diameter varies. Diameter get increases towards the mouth. Fine. So then there is a air chamber trapped between the throat and the diaphragm. So between the diaphragm, we can see in the diagram there is an air chamber between the diaphragm and between the throat. We can see that air chamber. So the chamber is lined with a sound absorbing material also. So sound absorbing material we can see in the diagram. Then the drive unit is similar to the direct radiating type, except that the paper cone is not present. You will not see here that any type of paper cone present over here. So it is similar to the direct radiating type, but only thing is that there is no paper as such. So as far as the cutoff frequency, before that we should realize that horn acts as a high pass filter. So the cutoff frequency is equal to F into in numerator we have C and A, that is 2 pi V. So where product of CA is nothing but a velocity of sound and the area of cross section of the throat. And what is V over here? Volume of a air chamber trapped between the throat and diaphragm. So air chambers volume we have to consider. So velocity of sound is important, area of cross section of throat is important, and volume of air chamber of throat. So this we should realize nicely. Then next, in terms of diameter of the mouth, the lowest frequency which can be reproduced by a horn means the cutoff frequency of horn is 170 upon D. So what is this D here? It's a diameter of the mouth in a meter. Now there is another case apart from these two equation, that is we have seen FC of both of horn as well as the FC of mouth. So at what happens at high frequencies, distance of different points on the diaphragm from horn will not be equal. Fine. So at when we take off a high frequency, the distance which is distance at different points on the diaphragm from the horn will not be equal, and causing the phase difference. Hence the resultant will be cancellation. So what it says, there is a phase difference at a high frequencies because of the different points from the diaphragm. So there will be cancellation. So to overcome the difficulties, a special chambers have to be deployed. What type of chamber is there? Let us see in the diagram. That is curved diaphragm we have shown. Then the horn over here and special chamber to compensate for the unequal distances. Fine. Then to improve the low frequency response, we need a horn of a large size. The length of the horn may be big as much how much it's 2 meters, and diameter of a mouth is 1 meter. So the length of the horn should be considered as 2 meters and the diameter of mouth should be 1 meter. Such large dimensions of the horns are unwieldy, and hence the horn structure is folded back in itself to conserve the physical space. So physical space also matters, a big one over here. And low frequency horn for high fidelity system is shown below. Let us see what the loudspeaker is. So we see the enclosure of a cone, sound waves which are going out, then exponential horn, and then the enclosure of for the cone. So directly we can see there is a cone, we can see there is a unit, there is enclosure for cone, sound waves, exponential horn. These three diagrams we can nicely draw for this particular horn type of loudspeaker. And the last ones are characteristics. Efficiency is very high, 30 to 50%, signal to noise ratio 40 dB, directivity changes frequency wise over here. Frequency response is 30 to 10 kilohertz, means 30 hertz to 10 kilohertz. Distortion is low, less than 5%. Impedance 10 ohm, and power handling capacity is much more than the cone type. It is about 100 watts. One loudspeaker can.